The people that I don't see here are Gabriel and Cody and Caitlin. No arguments? All right. I did get your first calculus-based homework assignment done. Now, you won't have an additional specifically calculus assignment probably for a long time if you have one at all this semester. You will again next semester. But there will be some calculus problems in the upcoming homework assignments based on what we talked about today. So there is not actually a calculus-based question on the homework assignment that's due tomorrow, but there will be on the one that's due on Friday. So that's how homework will be coming for calculus type problems. So today we're going to look at calculus of motion, more things that have to do with motion. So we've already seen things like this. That is, the speed is defined as the limit of delta x over delta t. And for instantaneous speed, it's as delta t approaches 0. But that's what calculus was invented for these situations where delta something is approaching 0. And so in calculus, this is the definition. Whoops, I'm on the wrong tool, clearly. This is going to disappear. How cool is that? That's the definition of, okay, it's not very cool because I want to keep it there. That's the definition of what dy is. It's the limit of delta y as delta y approaches 0. That's its definition. So we take that, and our definition for speed becomes just derivative. And we've seen this before, just reiterating where calculus comes into this motion very simply. And so similarly, acceleration, the limit of change in speed over change in time, or if you want to be fully correct, the limit of the change in velocity over the change in time is just dv dt. By the way, now that everyone's here, just a comment about the homework. I usually grade it out of 10 points for each of the little problems. This time I only graded 5 points out of each problem. I used to give 5 points extra credit for doing a good job of explaining the problem, and I kept that at 5. So that means that 3 or 4 of you actually got 55 out of 50 on this assignment. It's a little more extra credit, a little higher first homework grade, but it's not going to hurt you. I figure it won't, so I'm good with that. So most people did well on the calculus, actually a lot better than is common, which makes me feel good, confident about my students. There were a few people who had some issues with integrating and the limits. So if you had if you lost points there on the limits things, if you're confused about why you lost points, come see me so we can, get it cleared up. And if you understand, you're like, what was I thinking? Well, then now you know. All right. Getting to a practice problem, because I'm going to do, a lot of math in this class. Here's an example. Let's suppose we have an object that moves with this crazy function. 10 multiplied by times squared multiplied by e raised to the minus 0.7t. Obviously, the 10 is going to have units. What would the units of this 10 be? What are the units of speed? Meters per second. If I what are the units of an exponential? Unitless. So that means the units of 10 multiplied by t squared have to be meters per second. That's going to mean this 10 actually has units of meters per second cubed. So when you multiply it by time, that's not a 3, it turns out. I said the right word. There we go. When you multiply it by time squared, you'll end up with units of meters per second. And similarly, that 0.7 has to have units. What should the units of the 0.7 be? Actually, 1 over seconds. Because you have to have the exponent is unitless. And since time is seconds, that 0.7 has to be 1 over time. So there are units implied here. I didn't put the units in. But if it's going to have the right units, it has to have those if we're using the metric system. Okay, that wasn't the important thing here. That's why I didn't worry about writing in the units. How can you find the instantaneous acceleration? So somebody just blurt out, given this equation for the speed as a function of time, one-dimensional motion. How can I find the acceleration? Take the derivative. So I'm just going to take the derivative, and I'm going to do that on the next slide. How do I find when the speed is the greatest?
Acceleration is 0, and the jerk is negative.
Okay, when acceleration is 0 and the jerk is negative, he's absolutely right. How many people have heard the term jerk before as a scientific term? Obviously, everybody's heard you jerk. Aaron has heard it as a scientific term. So, since Cody obviously knows what it is, Aaron, what is it?
The third derivative.
Okay, the jerk is, she said the third derivative, that'd be the third derivative of position with respect to time. Or in other words, it's the rate at which acceleration is changing. And we in physics often don't worry about the jerk because, well, certainly in general physics we don't. In college physics we do a little because, we want to make sure people understand acceleration isn't always constant like we treat it in general physics. So he said if the jerk is negative, that is, if the acceleration is 0 and the acceleration is going to be going negative on both sides, then it must be at the max there. Or going, yeah. So most people, if they didn't know the terminology, would have taken just the general calculus definition and said, well, when the derivative of a function is 0, it's at an extrema. Now that extrema could be a positive, well, at an extremum. Extremum is singular, extrema is plural. It could be a maximum or a minimum, depending on the derivative. And for those who, didn't have the benefit of my teachers, I learned like this. If the second derivative is positive, it's a local minimum. If the second derivative is negative, it's a local maximum. Right? That's how my teacher taught me. And so with moving on. So the first derivative, when it's 0, it's a minimum or maximum. And the second derivative tells you which one it is. What happens if the second derivative is 0? You have a momentarily flat line, and it could be an inflection point, or it still could be maximum or minimum. So you have to go further if it's 0. Okay, then we have the next one. When is it at its greatest acceleration? How would you find that? Okay, I've never even heard the snap. I'm just going to trust you since you know the jerk. That must be correct. Where did you learn those terms? You read it?
Jerk, snap, crackle, pop from what I heard.
Scarily, I believe him on that. And then probably Rice Krispies if you want to keep going. Okay. And what if you wanted to find how far it travels in 10 seconds? You'd have to take the integral. Now, the integral of this is harder. In fact, I just did the integral already. It's already done on 2 slides from here. So let's do the first thing. Let's take the derivative to find the acceleration. So here's our function. And everybody's just been through the calculus. From now on, you don't have to be all explicit in showing your calculus. The first assignment is just to make sure you know how to do it. After that, I'm going to trust you could figure things out if you have the bones of what you're doing there. On the calculus, you still have to have explanations on problems. Don't think, this is a test problem with calculus. I'm only going to show the answer. Okay, so dv/dt. Obviously, this is the product of 2 functions, so I'm going to have to use the product rule. So I'm going to have 20t e to the minus 0.7t minus 7t squared e to the minus 0.7t. So that's my acceleration function. That was the product rule. So this first one was the derivative of the first. The derivative of 10t squared was 20t. And the second one had the derivative of the second portion. The derivative of minus 0.7t, or e to the minus 0.7t is just minus 0.7 times e to the minus 0.7t. So minus, Carrie, question? Because I had a 10 out front. So 10 times minus 0.7 gave me minus 10, or minus 7. It's a good question. So that's my acceleration. Rewrite it, or take that away so it doesn't mar it. Okay, so that's my acceleration. At time equals 0, what would the acceleration be? 0. Okay, acceleration is 0 at time equals 0 because we had t in front of both of them. As time approaches infinity, what's the acceleration going to be? Okay, I have an answer of 0. It's 0 times infinity, right?
Yeah.
When time was 0, it was 0 times 1, so we had no problem there. 0 times infinity, you'd actually have to use L'Hopital's rule to determine what the acceleration value is. In this case, once again, it turns out to be 0. It turns out to be 0 because the exponential function is a larger function than a polynomial function. If you look it up, you'll find that the exponential function is a polynomial of infinite rank, or whatever you call it. And so the exponential trumps the polynomial because it's an infinite polynomial. And so you don't have to use L'Hopital's rule if you've learned the rank of the functions. But if you haven't learned that, you use L'Hopital's rule. So we have 0 acceleration on both sides, and then we're going to have acceleration that's not 0 in between. So how do we find when acceleration is a max? Because that was a question. We already had the answer given to us on our method. Our method is going to be to set Tm for the time when we're going to have maximum speed to 0. Right? Take the derivative of the speed function with respect to time, evaluate at the time that gives me maximum acceleration at 0. Or not maximum acceleration, maximum speed. So that's going to be, now I'm going to factor what I can. I have 3 terms there. And so each one of those terms can give me a 0. What is the 0 associated with the first term? Or with the second term? Infinity. Or with the third term? If we set 20 minus Tm equals 0, that's 7 Tm equals 20, so 20 over 7. Now, again, we had those units to contend with, but it's going to give us zeros. So any one of these would be a time when the acceleration is 0, which means that it's a minimum, a maximum, or an inflection point. And so now we've gone through logically which one's which. What's going on at Tm equals 0 and Tm is equal to infinity? Nothing, basically. Those are minima at rest, and it's not going to go negative. And so what's left in the middle? It's got to be the maximum. Or it could be the minimum if the speed was always negative, but it wasn't. Right? Negatives weren't a possibility with our function. So this one here is the only true maximum. These two here were minima. So we were able to find the time when we have the maximum speed there. Now I've got a graph of this coming up in 2 slides, so we can look at that graph and compare the time. I forgot what else. When is the speed the greatest? When is it at the greatest acceleration? Well, if I want to find the greatest acceleration, we've already, once again, had the explanation there, so let's just do it. The acceleration was trying to look at my function. Yeah, only 2 terms. It looked like 3 at first. So there's the acceleration. So if I want to find when the acceleration is the greatest, and I'm going to call this time B because I don't want to use M again. So the first one, product rule. Second one, again, product rule. So I have that equation. Now I can simplify that. Question?
Would it be plus 14?
This one here.
The first plus 14.
This one here.
Yes, because you're bringing down the negative.
I'm bringing, okay, it was a positive A, and then I bring down the minus 0.7, so I have minus 0.7 times 20. This is plus 20 times minus 0.7 is what gave me the minus 14. And what I thought you were asking was about the next one.
Oh, yeah.
The next one was minus 7 times 2, because bringing down the 2. And the last one was minus 7 times minus 0.7, which gave me positive.
Okay, I just got confused where we were.
Okay.
Thank you.
Now I can simplify this, and so I will rewrite it. And once again, these would be at a specific time because I'm trying to set it equal to 0. So I can factor out e to the minus 0.7 TB. And I have 20 minus 28, whoops, TB, minus 28 because I had 2 minus 14 TBs there. And I forgot something and nobody corrected me. Where was my mistake there? I forgot my TB squared right here. So now, once again, if I go to solve this, what values could I possibly have for TB? What do I get from the first term? I get infinity again. And then the second one is going to give me 2 values because I have a quadratic. And you know what I'm not going to do? Solve the quadratic. But it's going to give me 2 values. And those 2 will be, I am guessing, a maximum and a minimum. Because it speeds up and it slows down, right? Okay, so that's how we find when we're going to have maximum acceleration. How far does it travel in 10 seconds? Somebody said, do the integral. Well, to do the integral, you can see from the black minus signs that I forgot to write my minus sign in the first equation, and then all of my work was consistent. And then I realized, wait, I forgot that minus sign. So I have black minus signs written throughout to correct for forgetting to put the minus sign at the very beginning. But I had to integrate this by parts twice. Now, at this point, since we're past the first assignment, there is another method available to you. What's that method?
Definite integral?
Well, no, it is a definite integral, but looking at an integral table, right? We've all taken calculus and we've learned some basic rules, and then we've learned ways that we could solve bigger, harder problems, but that doesn't mean that we have to do it the hard way every time. So you could just look it up in the integral table. In this case, I did it by parts because, well, I was at home when I was preparing this, because at home I have a faster computer and I have an up-to-date version of Microsoft Office. So doing things like changing the aspect ratio of the slides is easier, and the time taken to do any work on my class is faster. So I didn't have an integral table. I could have looked it up on the internet, right? But I just decided, let's do it by hand. It's a challenge. And then I got to my office and I have a program actually on my computer that will do the integrals for me. So I use that to check. So we have the first integration by parts gave me this equation here. And then I have integrating by parts again for the second term, which gave me this for the integration by parts the second time. And so when I put it all together, I ended up with this equation for position as a function of time. It's an interesting equation. And so then I could put in any old time and find what its position is at that time. Here's the graph of that function. You might wonder about this function. It actually is a significant function in physics, one that will be seen, I think, the very end of this semester. The Maxwell-Boltzmann equation, I believe, has this form. So here's what the equation looks like by the Maxwell-Boltzmann distribution. The only difference here is it would be temperature rather than time. It's still speed. So we can see, here is the time. Whoops, I'm on the erasing pin. Here's the time when it was at maximum speed, which, we didn't actually put, we did. It was 20 over 7. 20 over 7 is not that hard. It's a slight shade under 3, right? It's 2 6/7 if you wanted to do that fraction. And so that is indeed just a little bit under 3. So looks reasonable to me. And greatest acceleration, looking at the graph, how do you determine where the greatest positive acceleration is? The steepest positive slope. So that means my greatest acceleration should have been somewhere right about here. My minimum acceleration should have been somewhere right around here. And so those are what we would have gotten from the two roots of the quadratic. And you can see the acceleration, because the velocity is flattening out, if you go out far enough, the velocity is essentially constant at 0. And so the acceleration is 0 because the velocity is not changing. When I did this, apparently I didn't see that white writing in the background. I just put a new title over whatever I had before. I saw that afterward and was a little embarrassed. And so I tell you all about what I'm embarrassed about, just in case you notice it and say, hey, I wonder what happened there. That integral that we did has a graphical interpretation. I don't know about you guys. You're still in college. I took calculus and, well, things were different back then. I took calculus and physics at the same time. And so in calculus class, they're trying to teach me what a derivative and integral is. In physics class, we're using them. And in the calculus class, I could do math really well. And so I just did the math. And it didn't make any sense to me. It was just doing math. And then in physics class, that's where suddenly the math started making sense. That it wasn't just, going through equations and getting an answer and feeling good about myself because I could do math. Part of that presented itself. You can all laugh at me now or later. we had one day where the textbook introduced the antiderivative, right? It's the reverse of a derivative. And then the next section, the textbook talked about integrals. And so in the section where it talked about the antiderivative, it talked about doing essentially, the method here. And then the next one, when it talked about integrals, it talked about a different method. And I thought the two things were separate things. And so when I looked at problems, our textbook sometimes would say find the antiderivative and sometimes find the integral. And never in my mind did it click I was doing the same thing. I used one formula for antiderivatives and one way for integrals. And then when I found out the same, I felt so stupid because the integral stuff was so much easier than that laborious antiderivative way I'd learned. But in physics class, it all started to make sense. We had things like this here. I honestly remember my teacher, big beard, Barry Grames. He liked to write on the board. ZZ Top was here because of his beard. He'd been a physics major in undergrad and then became a math major, so he was pretty much doomed to being a nerd. Anyway, he drew nice pictures like this showing a graph and talking about, now if we wanted to find the area under the graph, we could make these rectangles, and there's different methods of making the rectangle, the center one, or where the leading edge is on the line or the trailing edge is on the line, and the accuracies of each. But in the end, you get that area of the rectangle and you add up all the little areas of the rectangles and it gives you the integral. It made no sense to me except for he said these words. And then in physics, it started really making sense because I could look at something and say, well, look at this picture. The area that is enclosed by this shape here is the distance that it's traveled, because the integral is my function times dx. So it's a height times a width if we make the graph. And then the integration is summing, right? The integral sign just means sum them up from the beginning point to the ending point. And so if I take all those little things, this picture is perfectly explaining that idea, but it wasn't until physics class that it made sense to me that I can just find the area under the curve. That's what I'm doing when I'm doing an integral. So the distance that's traveled is the area under the curve. So if you look at this, compare the distances that it travels before peak speed to the distance it travels after peak speed. Which one's bigger? After, right? You can tell just with a glance factor because the area after that peak is bigger than the area before. So with that information, if I were to ask you what at what time does it have the average speed, when would you put that time for the average speed? Now I know, granted, you could get two answers because of the shape of the curve, but the average speed is going to be somewhere, like here. And so the time for the average speed would be something like that. And how do you place that line? Yeah, where the distance on one side is equal distance on the other. Okay, so the graphs can carry a lot of meaning. Now, another practical example, one that's a little more fun. These are true numbers. A top field dragster has a peak acceleration of about 5.6 Gs. How many people have been in an acceleration above 2 Gs? If you don't know you have, you probably haven't. If I went to the Houston Space Flight Center, and they have a ride where they spin you up to about 4 Gs, which is cool. Now, you've been on spinning rides in amusement parks, and you may have gotten up to 2 Gs or so. But by the time you get up to 4 Gs, I was like, wow, it's getting hard to breathe. Because they actually tip you, so you're not just having your throat collapse, but you've got to still have your lungs expand a little, right? And so it was actually really cool, and gives you an idea of what it's like. Those top fuel dragsters are pulling 5.6 Gs. That's really rough on the body, right? And you've got to sit there and steer that thing. Right, because what you don't want to do is go veering off, and you roll and things. I was reading up on this morning, and just some numbers to help people feel more about what the dragster's like. Okay, for top fuel, because they go so fast, they limit them to only going 1,000 feet. Right, that's the only length they do because of the danger of going at high speeds. And so, if you had a nice new Corvette and you got a nice long run up, so you're going 200 miles per hour at the time you pass the top fuel dragster, and he starts at the time you pass him, who's going to win the 1,000-foot race? Him in a landslide. When you think about that, the acceleration is pretty incredible. And the top speed for a dragster on that 1,000-foot race is 330 miles per hour, which, it's kind of cooking. So we could approximate that the acceleration is going to be strongly dependent on the speed, because as you go faster, you have more wind resistance, and so you have more that's opposing you going faster. It slows down your acceleration. So I made a simple equation that says acceleration is equal to your peak acceleration times 1 minus your speed over the maximum speed. It's a reasonable approximation. What we're doing here is we're just trying to model what's going on with a top fuel dragster. So if we take that equation, can we find the speed as a function of time? Notice this was acceleration as a function of speed. Can we find the speed as a function of time? The answer is obviously yes, or I wouldn't have asked you. But then the bigger question that everyone's probably contemplating is how? How, great hell, do I find this acceleration or this speed as a function of time? We've actually done something like this already. What we're going to have to do is replace either A or V with the calculus definition. Which one do you think would be simple or actually doable to replace, the acceleration or the speed? Okay, I had some of both answers. The correct answer, and that means everybody's thinking. The correct answer is the acceleration, because acceleration is dv dt. So if I replace acceleration with dv dt, I have two variables, v and t. If I replace the speed, I would have had dx dt, and I would have had acceleration as one variable, x is one variable, and t is one variable. I would have had three variables. And so that's why replacing acceleration is the way to go about it. So let's do this first part. Let's find the speed as a function of time. So here's my acceleration, which is equal to dv dt. Now we learned in our first lecture the next step. Do you remember from that first lecture what the next step is? Excellent. Separation of variables. So I'm going to separate variables. The two variables are v and t. I need them both in the dv and the dt, both in numerator position. So obviously, I first multiply by dt. I'm going to reverse the order here. So I'm going to have dv is equal to a0 but that's not done. What's wrong with this if I'm trying to separate variables? Which one?
Your V's.
I have V's on both sides of the equal sign, so I ain't done. So now, it's just like algebra. You just have to look at this. How can I remove all V's from the right-hand side? Divide. What if she had said subtract? It's not how it works. She wouldn't have said it because she knows that's not how it works. If I had subtracted, then I would have had, instead of dv multiplied by v stuff, it would have been an additional term there, but it still would have had dt multiplied by it, right? That wouldn't work. And if I just tried dividing both sides by v, what would have happened? I would have had a 1 over v term. Well, that didn't get rid of the v on the right-hand side. Just made it 1 over v. So I have to go like this. So now I have the equation dv over 1 minus v over v max equals a0 dt. Now it's completely separated. I have two sides of the equal sign that are independent of each other but equal. Since they're independent but equal, I can integrate one over its variable, integrate the other over its variable, and they still have to be equal. So I'm going to add my integration sign. I do need to have limits on this. My limit will be from v initial, a drag racer, how fast to go in and start. Okay, so from v initial equals 0 to v final, which we actually have a value for, but I'm not going to put the number in here. I'm going to get an equation for v final. From time initial, what should my time initial be? Because why would you have it in anything else? You don't start timing the race and then, okay, when we get to pi seconds, you guys start, right? That would be kind of ridiculous. To t final. Now, the right side of this is downright trivial. The left side, well, not as trivial. What would, who wants to be a guinea pig? What would you, Caitlin, what would you do to integrate the left-hand side? This is not one you would likely look up in an integral table. It's generally too trivial to be included in the integral table. Uh-oh. Well, let u equal 1 minus v over v max. And as you probably learned, there is kind of an art to deciding what the u is. In this case, it was real simple. Just the stuff that dv is divided by. And so if that's the case, then du is equal to, of course, derivative of 1 is 0, minus, now, are you guys familiar with doing derivatives this way, where it's not with respect to anything? Yeah. Okay. Because sometimes that will be confusing to people. You know, I can do d dv, but I can't just do d. Well, when you just do d, you just have a d on the variable, and otherwise you follow the same rules. So it'd be dv over v max. V max is a constant, so there's no product rule or quotient rule in this case. Now I'm going to take this and solve this second equation for dv in terms of du. Why? Because I want to substitute for dv in my equation. And so putting that substitution into my equation, I have the integral from 0 to v final. I put from 0 to v final. I can't do that. Why can't I do that? Because I just changed the variables. So I'm just going to put u initial to u final of minus v max du over u What is u initial here? Given that u is defined as 1 minus v over v max, if I put in v initial, what is u initial? 1. Because it's going to be 1 minus 0 over v max. So that's just u initial is equal to 1. And u final, using the same rule, that's going to be equal to 1 minus v final over v max. Now, one last thing I'm going to do before I integrate the left side, and you don't have to do it now, I just like to, is divide both sides by minus v max. I like to do it now, so I'm just doing the integral of du over u. without any minus signs or other terms. So now integral of du over u is one that you, Gila, question.
Is Vmax a constant?
Vmax is a constant, that's right.
Can you just do the integral?
Yes, I did. I actually put it in front of the integral because it's constant. You couldn't divide it out like I did once you've thrown the integral signs on if it wasn't a constant. Now, before you put the integral signs on, yes, you could have. Any other questions?
So what would add up here then?
I just divided both sides by minus v max, so the left side now is just integral from u initial equals 1 to u final equals 1 minus vf over v max du over u. So I just divided it out to get that form because I like to have the du over u without anything else multiplied by it. It's a personal preference. So now we do the integral on the left-hand side, and like I said, it's one that you just have memorized, and that's going to be natural log of u final over u initial. So 1 minus v final over v max divided by the u initial, which was 1. Okay. You might look at that and say, why does he have this stuff divided by 1? Just so we keep in mind that we did apply our limits. We did the final minus the initial. Since they're natural logs, final minus initial is natural log of the final over initial. That's not a T. All right. Simple enough. I want to solve for v final, but it's in a natural log. So how do I get rid of a natural log? E raised to this is equal to e raised to that. And e and natural log are inverse functions, so e raised to the natural log is just going to be the argument of it. So I'm left with 1 minus v final over v max is equal to e raised to the At this point, I'm going to drop the finals. I'm outside of the integral process now, so I'm not breaking any math rules by renaming v final as v and t final as t. And now the last step is to solve this for v. So to solve this for v, I'm going to add this to both sides to move it across, subtract this from both sides to move it across, and then multiply everything by v max. So I'll have v is equal to v max times 1 minus e to the minus a0 over v max t. So there's my speed as a function of time. I started with speed with acceleration as a function of speed, and now I was able to find speed as a function of time. Well, now that I have this, the next step is kind of trivial. What's the acceleration as a function of time? Anyone?
Can you repeat the question about?
Now that I found the speed as a function of time, how do I find the acceleration as a function of time? I just take the derivative. So taking the derivative of this is going to be, okay, v max is a constant, so I'll ignore it. Derivative of 1 is 0, minus derivative of this is going to be bring down a minus a0 over v max. Don't do that. So I believe I did that derivative correct, Lee. And yeah. And so I have the acceleration as a function of time. I could find the position as a function of time from this velocity equation. How would I do that? I would have to replace v with dx dt, separate the variables, and integrate. I only have 5 minutes left, so I'm going to skip this second slide that was for doing that and go to the solution. What you find when you integrate that velocity equation up to find position is that the position is Vmax multiplied by time, a linear term, minus Vmax squared over A0, a constant, plus Vmax squared over A0, e to the minus A0 over Vmax t. That's a fine function. You can find the position at any time from it. But my problem actually asked me to find how long, I think it asked to find how long it would take to cover 1,000 feet or 305 meters in 3.7 seconds. So, or actually not in 3.7, that's the true time. How long will it take? And so if I want to find from this equation the time, there is no analytical solution. You cannot take that equation and solve it for time. It's physically not possible. I have watched this clip, and my son and I joke about it too much that I almost say impossible. Right? You guys probably seen Ralphie Wiggum. What? Me fail English? That's impossible. Okay, so, but this is not possible. So we have to find a way to solve it that's not analytic. That is, it's not just pencil and paper, it's doing something else. And this is where in physics we have 3 things that you can specialize in physics. You can be an experimental physicist, that's what I am. You can be a theoretical physicist. That's somebody who does analytical work and thinks about the theories, right? I did experimental stuff to test and see what happens. And then there's a third one that's relatively recent. It's evolved in my lifetime, and that is a computational physicist. Somebody who uses computers to do calculations about what's going on. And sometimes that's the only way we can treat things. We have a system that's way too complex for us to be able to do all the calculations. Or we may have, a chaotic system. You guys have heard the term chaos. You probably don't know what it means. A chaotic system is not a random system. How many people thought chaotic meant random? Wow, you all knew it didn't mean random. That's impressive. Most people think chaotic means random, and it's not. A chaotic system is a system that's so complex that we cannot accurately predict the future after a certain amount of time. If you have a little uncertainty, like let's say you have a 1 in a billion uncertainty, you might be able to predict the future for, 5 minutes. But that 1 in a billion part of uncertainty, after 5 minutes, it becomes such a big error in your calculations that you just can't predict what's going to happen anymore. That's what a chaotic system is. And so computational physicists will write computer code to calculate what's going to happen, and there are ways to treat these systems to find order and meaning in a chaotic system. Okay, so this one here is something that's simple, something you and I can do. We can take this equation and say, okay, I'm going to make the left portion of this equation, I'll call this A. And the right side of the equation, I'll call B. Now notice, because of the equal sign, they have to have the same units. In this case, the units are unity. There are no units on either side. And I am going to make a spreadsheet or a computer program that calculates A as a function of time and B as a function of time, and then find the time when the two are equal. So I did just that. I made a spreadsheet, and then I graphed from the spreadsheet, and here are the graphs. So the first one is showing the entire race, going from 0 time and showing A and B. So here we have, this was A, my left side, B, my right side, and the time when they're equal is right here. Well, to get it more carefully, I just changed my delta T in my spreadsheet, and I was able to find that it's 4.81832. It's actually 4.18317 is as far as I calculated it. And so that's the time that it would take with our model for the dragster to complete the race. That's 13% longer than reality. And this calculates the final speed in the race of 116.7 meters per second. But what we had said from the beginning was the top speed at the end of the race is 148 meters per second. So this model did not end up at the maximum speed. And it took too long. So how could we improve this model to make it give us a better fit? There are lots of things you could consider. One is they do go through some gears. And so you're going to have a non-smooth transition acceleration when you go through the gears. And the engines, of course, have a different torque in different RPMs. And so that makes a difference. But of course, the reason they use the different gears is to try to get the maximum torque throughout. And so those two actually kind of work together to try to make our model more accurate. Because ideally, they'd want maximum torque throughout the race. And so their gearing is to try to accomplish that. But I made one really big flaw in my initial assumption. I almost underlined it at the beginning, but I thought, well, I better let people think about it. Can anybody think about the fundamental flaw that I made in my assumption? Because our time is up, actually we're 2 minutes over. Shoot, I thought we were a couple under. Because our time is up, I'll tell you the fundamental flaw. I said that this maximum speed that they attain in 1,000 feet is the maximum speed of the dragster. Well, that's not true. It's still accelerating. It could have gone faster. Using this model, it was still accelerating at about 1.3 Gs at the end of the race. So this model would say, no, we didn't reach the maximum speed. So I went back in and I just randomly tried a couple numbers. And if I had set the true Vmax at 300 meters per second, saying the dragster could reach a maximum speed of 300 meters per second, twice what it reaches at the end of 1,000 feet, then it gives you both 148 meters per second for its speed at the end of 1,000 feet, and it gives you that 3.7 seconds for the 1,000 feet. So our model actually perfectly matches those numbers if we have the right speed for its maximum speed. So that's part of what modeling has to do, is find those values. Okay, this was my last slide, and we are 3 minutes over. I'll see you all for lab.